Hi everybody, my name is Cristian Morbidoni from University of Pescara in Italy. I'm going to present a research work done in collaboration with some colleagues from the University of Ancona. In this work, basically, we leverage Ngram's neural embeddings to try to improve the performances of deep learning based detection of domain generation algorithms. So let's start with a little description of the scenario. All of you know what botnet is. It's a network of malicious softwares, of malwares, that are coordinated in their collective action by a command and control server, the CNC server. So the process starts with the attacker using domain generation algorithm. He generates a number of one or more domain names, and then he registers them. Then he embeds the same domain generation algorithms into the bot. So when they are spread into the network and they are active in an infected machine, they start to issue a number of DNS calls. They generate a great number of domains with the same algorithm used by the attacker. And they eventually, at a certain point in time, they discover the IP address of the CNC server, and the malicious action, let's say, starts. So being able to detect suspect domains even before the right IP address is discovered is important to implement countermeasures. For example, redirecting the bot to a on-a-pod server, or using DNS sinkholes techniques, and so on. There are several approaches to detect DGA-generated domains. We can distinguish between approaches based on the analysis of DNS traffic, for example, analyzing NX domains responses, and those based on the analysis of the actual domain name only. For example, traditionally blacklists of domains were used, but this is an impractical approach, and recently machine learning has been applied a lot to solve this problem. Both feature-based machine learning approaches and deep learning based ones has been investigated. In practice, in real-world systems, these techniques are usually combined and integrated into more, let's say, ensemble detection systems. And we can generally say that there is a class of DGAs which is hard to detect in practice, which is based on vocabulary word combined to form domains which resembles the actual domains, let's say embedding domains. Let's try a little quiz. Which one is a DGA generated domain name? So it comes out that the first one is a DGA domain, the second one is genuine. There are two relevant machine learning tasks in this context, which is a two-class classification problem to tell if a domain is genuine or algorithmically generated from some DGA, and then a multi-class classification problem, which is about telling exactly what algorithm generated a given domain, what DGA family. And we target this problem here, even if in our architecture we also perform a two-class classification, as we see later. We can say that according to a recent literature, the deep learning approaches are performing better than the other ones, and often recurrent neural networks architectures like LSTM-based ones are employed, perhaps mixed with attention mechanism or CNN networks. And the problem is that they work well with big training datasets, and extracting big labeled dataset from a real traffic is challenging. So usually the technique used is to reverse engineering the DGAs and generate a lot of labeled training sample. So in practice, this is not always possible. For example, if you have a new DGA enter the scene, you have a few clues, few examples of these DGA. So it is interesting to understand how these approaches performs with small datasets. Now, as a DGA classification problem from domain names can be cast to a text classification problem, basically, and we all know this is today dominated by word embeddings. So the question we ask is, can we learn some embeddings that represents n-grams in a domains? Perhaps we learn from real domain names. And are the hidden semantics encoded in these embeddings useful to improve the performances of the deep learning models when small training data sets are present? And two secondary questions are, if there is an improvement, how this changes with the growing size of the trained data or across the different DGA types that we have. To try to answer our questions, we experimented with the 25 DGA dataset, which is comprised of 25 different DGA families plus genuine domains taken from Alexa. And it includes about 14,000 domains for each DGA. We can say there are different types of DGAs. We have time-dependent DGAs where the seed used to generate the domains is based on some time-dependent data source like Twitter, for example. And then we have a time-independent DGAs, and then we have domain generation algorithms which are based on vocabularies, English words, or even Latin vocabularies. And finally, banning domains, which you see are quite similar at a first glance to the vocabulary-based domains. Then, in order to take into account the dimension of the dataset sizes, we performed a stratified slicing of the dataset, obtaining data sets of different sizes, ranging from 4K, so 4,000 domains, to 338K domains. In the case of the smallest domain names dataset, we have only 75 domains to learn from for each DGA, while in the biggest one we learn from 6,000 domain for each DGA. And in this way we have the opportunity to see how a possible improvement in using embeddings varies across different sizes of the training dataset. Next, before feeding our model with domains, we represent them as a bag of n-grams. So basically, we move a sliding window across the domain to capture 1 grams, 2 grams, and 3 grams. As you see, for example, this domain roomkill.net is decomposed into overlapping series of 1 grams, 2 grams, and 3 grams. The next step is learning the actual n-grams embeddings. We employed the skipgram model using the fasttext implementation, which is quite easy to run. And we did it on top of the Majestic Million dataset, which includes 1 million genuine domains. So these domains are transformed into a bag of n-grams representation, and then after the skipgram is trained, we obtain n-grams vectors of 128 elements each one. So then we fed these vectorized n-grams representations to a deep learning model, which is an adaptation of the LSTM-based framework proposed in the paper you see at the bottom of this slide. Our system is composed by the unsupervised embedding learner, which you see on the top, as the previous slide. So we use the skipgram model to obtain these vectors, and we use them to initialize the embedding layers of two LSTM networks. These two networks are arranged in cascade, so we first perform a binary classification, and if the prediction is Banning domain, we take it as good. Otherwise, we pass it to the multi-classifier, which assign it to one of the 25 DGAs. So we use the same architecture to obtain four models where the same neural architecture is used. The difference is that in our baseline model, the embedding layer is initialized in a random way. This is the implementation from the paper cited in the previous slide. And then we used instead the pre-trained 1 grams, 2 grams, and 3 grams embeddings to initialize the embeddings of the other three models. So with these three models, we run experiments training and cross-validating on the different slices of the datasets that we discussed before, so from the smallest one to the biggest one. And in this slide, we see the overall results in terms of macro averaged F1 score across the 25 DGA classes plus the Alexa. We immediately see that we do have an improvement in performances, in particular where with the smallest dataset, the pre-trained 2-gram models provide a 1.5 improvement in accuracy. But we also see that the performances, they're quite the same overall when the datasets become to be big enough. So this seems to confirm that we have an improvement overall using embeddings, in particular 2 grams embeddings. We can also break down the results across the different DGA types. We can see that the results obtained detecting legitimate domains they are quite good. They are always over the 80% of F1 score. We also see that the baseline have problems with the small datasets, so we have very poor performances, specifically for vocabulary-based DGA and also for time-independent DGAs. While we in general have an improvement in all the classes applying the pre-trained models, and in particular, if we look at the vocabulary-based DGAs, the best one is the pre-trained 3G model, which seems to capture more words, maybe, which are used in this kind of domain generation algorithms. So we might ask if these good performances, relatively good, let's say, are due to the pre-trained embeddings or to the size of the n-grams considered, given that the best performing is the 3-gram model. So the baseline here is built on 1 gram. So what would happen if we randomly initialize the models with the 2 grams and the 3 grams? In these charts, we compare the random initialization with the pre-trained embeddings-based initialization, both in the 2-gram and 3-gram models. And you see that, especially for vocabulary-based DGAs, we always have an improvement. And in some cases, this improvement also holds when the data sets are bigger, even if the improvement is smaller, of course. So we range from a 0.2 improvement in F1 score in the case of 2 grams, and this is even bigger in the case of trigrams. But we also observed that a pre-trained trigram model doesn't perform so well overall. So if we look at the overall results of the trigram model, you see that for bigger data sets it seems a bit worse than the baseline. Well, finally, I would like to quickly show this table of detailed results across different classes obtained on the 4K dataset, so the smallest one. We can say that if we only look at the average score, the best model seems to be the 2-gram, but we also see that different n-gram based models perform well for different DGA families. For example, you see that Masnu, one of the vocabulary-based one, is better detected by the 3-gram model, while, for example, Pashto and CryptoLocker are best detected from the 2-gram models, while the 1-gram models does best for Rambius and SIMDA and so on. Does different embedding types work well for different DGA types? So this suggests possible improvement. And actually, as part of future works, we plan to integrate, to ensemble these different models, so combining different kinds of embeddings to further improve the results. We already conducted some experiments and it seems a promising direction. Then it is also interesting to investigate specifically a few-shot learning problem or zero-day DGA detection, where you have very small data to learn from, like units of examples. So with this I concluded my presentation. Thank you for your attention. This is my email, and have a good conference.